Please subscribe, follow and like engineeringall.com.
In this video, we will be discussing about aircraft engines, also known as jet engine or gas turbines, their various types, parts, and components, and how they work. Aircraft engines are such an integral part of the operation of aircraft. In the early days of aviation, the absence of the development of propulsion was a major hindrance to the development of aircraft. The aircraft that were made then were only gliders that couldn't go a far distance, since they could not generate their own thrust. Things changed when aviators realized piston engines could also be used in aircraft. This idea was further built and ushered in the development of more sophisticated engines exclusively for use in aircraft, gas turbine engines. The term aircraft engine commonly refers to gas turbine engines that most modern aircraft use, although there are still piston propeller engines being used in light aircraft today. In this video, I will be explaining the workings of gas turbine engines. Aircraft engines are also called the power plant of the aircraft. This is a befitting name since they not only provide the thrust needed to move, but also drive generators that power the aircraft's electrical system and in turn, the aircraft's systems. The different types of gas turbine engines are: turbojet engine. This is the base type of gas turbine engine. It is the concept on which other gas turbine engine concepts were built. It works by accelerating a relatively little mass of air a lot when compared to a piston propeller engine. The stream that enters it is accelerated from free stream velocity to a very high velocity after leaving the exhaust. Turboprop engine. This is a crossover between a piston propeller engine and a turbojet engine. The piston propeller has a propeller being powered by a piston engine, which is also found in cars. In a turboprop engine, the turbojet engine replaces the piston engine. Turboprop engines are found in lighter aircraft, e.g. commuter aircraft. Turboshaft engine. This is the engine used in helicopters. Its configuration is similar to that of turboprop engines, except that the exhaust gases are allowed to expand fully and drive the shaft, which turns the rotors. In a turboprop engine, the exhaust gases are used to produce residual thrust instead. Turbofan engines. This is the engine used by most airliners, i.e., passenger aircraft. It is essentially a turbojet engine with a ducted fan. In this engine, there are two streams of air: the cold, or bypassed, stream, which is so called because it is bypassed by the fan through the duct and does not undergo combustion, and the hot stream, which goes through the main engine, gas generator, and undergoes combustion. This makes it suitable for use in such large, long-range aircraft as it is able to provide much more thrust than a turbojet engine. The term gas generator refers to the combination of the turbine, S, compressor, S, and combustion chamber of the engine. A turbofan engine accelerates a little mass of air by a lot through its core, and a large mass of air by a little through its bypassed area. The bypass ratio, BPR, of a turbofan engine is the ratio of the cold stream mass flow rate to its hot stream mass flow rate. Generally, the higher the BPR, the higher the thrust produced. PW100 turbofan engine, production by Pratt & Whitney. In this video, I will mainly be talking about the turbofan engine, its composition, operation, and structure. Parts of a turbofan engine. Turbofan engines have several parts that work together to ensure optimal production of thrust and also power for the entire aircraft. These parts are complex as they are made up of smaller components, but they each have specific functions. In this part of the video, I will explain the functions the main parts of the engine have and how they operate to achieve them. The main parts of a turbofan engine are: 1. Air intake section. The job of the air intake is to allow an airstream to flow into the engine as efficiently as possible. The air intake is at the front of the engine's nacelle. A simple and commonly used intake in subsonic, meaning flying at speeds below the speed of sound aircraft, is a circular cross-section termed the pitot intake. Pitot intakes maximize the airflow into the engine at such speeds. Beyond the sonic speed, the efficiency of such an intake drops due to the formation of shock waves. Passenger aircraft are generally subsonic. The shape of the intake duct is divergent, meaning the area increases as you go from left to right. When the area increases as such, the velocity of the airflow reduces while its pressure increases in accordance with Bernoulli's principle. Compressor. The job of a compressor is to raise the airflow entering at much higher pressures. There are two main types of compressors: axial and centrifugal, radial. Axial compressors have their blades coming out along an axis, while centrifugal compressors' blades have their rotating blades arranged in single circles. Centrifugal compressors are virtually obsolete in modern turbofan engines since axial compressors are a lot more beneficial in that they allow for much higher pressure ratios and increased mass flow. The term pressure ratio refers to the ratio of the pressure of the airflow that exits an engine section to the pressure that enters it. Axial compressors have several stages that alternate between stationary vanes and rotary blades. The airflow which enters the compressor is first accelerated to a higher velocity by the rotary blades and then diffused by the stationary vanes. Before the airflow enters the combustion chamber, a component called the discharge diffuser converts any residual velocity to a pressure rise. Modern turbofan engines have between 2 to 3 compressors. The more compressors, the more compression is done, and even more efficiently since compression is done in tiers: low pressure, intermediate pressure, and high pressure. Combustion chamber. It is also called the burner. Here, the fuel is fed through fuel spray nozzles into the chamber so that the airflow, which mainly comprises oxygen, can burn it. The higher the temperature of combustion attained, the more the air expands and the more efficiently thrust is produced. Nonetheless, the structural integrity of the turbine, into which the hot air flows afterwards, must be considered. This means the combustion chamber temperatures must not be excessive. Most modern turbines cannot work with airflows whose temperatures exceed 700 degrees Celsius. The duct just before the inlet of the combustion chamber is divergent so that airflow can be slowed down to a speed that sustains continued combustion. The pressure at the end of this duct is the highest in the entire engine. Afterwards, there are pressure drops due to expansion. The combustion chamber consists of a flame tube, which is the largest part of the chamber, swirl vanes, a snout, and a flare. The flare divides the airflow into primary, secondary, and tertiary sections. The tertiary airflow, which makes up about 60%, is used to cool down the exhaust gases to a suitable temperature. Modern engines additionally incorporate other technologies for cooling. Turbine. Turbines can be said to do the reverse job of compressors. Compressors compress the airflow while turbines expand the mixed airflow that passes through them. They are responsible for extracting most of the energy from the airflow from the combustion chamber as it expands. This energy is then converted into useful work to drive the compressors via a shaft that connects them, as well as the gearboxes which drive the accessories. Because of this energy extraction and the fact that energy must be balanced, the velocity, i.e., kinetic energy, of the airflow will decrease. The remainder is what provides thrust. The turbine has a stator section followed by a rotor section. The larger the diameter of the turbine, the higher its power output. However, the diameter increase must be restricted so as not to induce more drag and impose excess stress, due to the centrifugal force produced, on the structure. Instead, to maximize the turbine power output, multiple stages are used. The efficiency of the turbine increases with its angular speed, RPM. Modern turbines are made of much stronger materials and typically have cooling adaptations in their design that enable them to withstand the extremely hot temperatures of the air from the combustion chamber. A thermocouple is fixed in the turbine so that its temperature can be monitored. The number of turbines in an engine matches the number of compressors, so there are also low pressure, intermediate pressure, and high pressure turbines. Exhaust section. As the name implies, this is where the exhaust gases from the turbine leave the engine. So as to maximize the production of thrust, the airflow exiting the turbine and entering the exhaust section must be released in the right direction and with the best possible speed. For engines that are a part of the airframe, aircraft main structure, a secluded passageway must be provided for the exhaust to exit the engine. These passageways are heavily insulated from the aircraft fuselage. The jet pipe must not be too long so that the exhaust flow does not cause turbulence and reduce the effective thrust produced. There is an exhaust cone fitted to the end of the last turbine disc. This makes it possible for the airflow in the nozzle to be divergent even though it has a convergent shape. A cone in the exhaust section acts to reduce the speed of the exhaust and prevent it from flowing across the face of the preceding turbine disc. This reduces turbulence at this part of the engine and prevents overheating of the disc. Fans. This is the component that sets the turbofan engine apart from the turbojet engine. Turbofan engines used in aircraft typically have axial flow fans. This type of fan moves the airflow along its axis. The shape of fan blades enables them to generate a lift force as they rotate. This lift then pressurizes the air, thus the fan is loosely regarded as the first compressor. The pressure rise after the fan works on the airflow is much smaller than compared to the compressor though. The fan blades usually have twisted shapes as it reduces the formation of shock waves, vibration, and noise in the engine. The twisted shape also allows some air to enter the compressor directly. The bypass section of the engine doesn't need a direct flow of air. The S shape of the blade tip helps to ensure the air doesn't get thrown out due to the centrifugal force generated by the fan. This way, the air flows closer to the hub and has a better chance of entering the engine. Turbofan engines with high bypass ratios have bigger fan blades. The high bypass ratio allows for more fuel-efficient thrust production, and quieter engine operation. This is especially appreciated in passenger aircraft engines. The fan disc is the central hub of the fan to which blades are attached. It is rotated by a shaft which is driven by the turbine. In a multi-spool engine, it is the low-pressure turbine that drives the disc. The discs are typically large and heavy. The structure must be so strong that it is able to withstand the centrifugal force imposed by the blade rotation. Materials with higher strength-to-weight ratios are preferred. The fans must be constructed with materials that are very corrosion resistant in order to preserve their structural integrity. The fan blades are exposed to the air so contaminants in the air can more easily corrode them than other parts of the engine. For this reason, some fan blades are constructed with titanium, a material with extremely high corrosion resistance. The material also needs to be impact resistant since the fans can be exposed to a lot of foreign object debris, FOD, and bird strikes. Accessories. These include the hydraulic, electrical, and pneumatic systems to which the engine supplies power. Some of the hydraulic pumps in the aircraft can be engine-driven. The generators are also driven by the engines. Fuel pumps and oil pumps will also be driven by the engines. An accessory gearbox drives all these accessories. It is connected to the compressors through a shaft. For engines with more than one compressor, the accessories are divided into two or more groups. The group of accessories that directly affect the performance of the engine, such as the fuel and oil pumps, is driven by the high-pressure compressor. The secondary group of accessories is driven by the low-pressure compressor. This setup comprises multiple shafts to drive the different gearboxes. Indeed, the turbofan engine is a sophisticated machine befitting of the larger, longer-range aircraft we have in the modern day. Advancements to aircraft engines are still being made, with electric and hydrogen.
For watching, please hit the red button to subscribe for more videos. Please follow and like engineeringall.com in all social media.